Burbank, California. Spring 1941. Inside Lockheed Aircraft Corporation's engineering offices, a young engineer named Clarence Kelly Johnson stared at a problem that had killed more promising aircraft designs than enemy fire ever would. The twin-engine fighter prototype sitting in the experimental hangar could barely climb above 15,000 feet without gasping for air like a drowning man. At 20,000 feet, where modern air combat was increasingly being fought, the engines produced less power than a crop duster. The Army Air Corps had given Lockheed one last chance to fix this catastrophic flaw, or the entire P-38 program would be cancelled. Johnson's solution would be called reckless, unnecessary, and absurdly complicated by nearly every aviation expert who examined it. Within 2 years, that same solution would transform the P-38 Lightning into the most feared fighter in the Pacific sky. If you're enjoying this deep dive into the story, then hit the subscribe button and let us know in the comments from where in the world you are watching from today. The fundamental problem facing Johnson wasn't unique to Lockheed. Every piston engine in 1941 faced the same cruel reality of physics. Air gets thinner with altitude. Thinner air means less oxygen. Less oxygen means incomplete combustion. Incomplete combustion means power loss. At sea level, a typical Allison V1710 engine could produce 1,150 horsepower. At 20,000 feet, that same engine struggled to generate 600 horsepower. The mathematics were brutal and unforgiving. For every 1,000 feet of altitude gained, a normally aspirated engine lost approximately 3% of its power. By the time a fighter reached 25,000 feet, where German bombers operated over Europe, and where Japanese reconnaissance aircraft surveyed Pacific targets, the engine was producing less than half its rated output. American fighters climbed slowly to these altitudes, arrived exhausted and underpowered, and found themselves easy prey for enemy fighters that had conserved energy by starting from higher bases or by being specially designed for altitude work. The British had attempted to solve this problem through careful engine management and conservative climb profiles. The Germans had developed direct fuel injection systems that improved efficiency at altitude. The Japanese had created lightweight airframes that required less power to maintain altitude, but these were incremental improvements, tactical adjustments to an inherent limitation. Johnson was convinced that incremental wouldn't be enough. The P-38's twin-engine configuration gave it range and redundancy, but also weight. The aircraft needed both engines producing full power at high altitude just to maintain competitive performance. Losing half the power output at 20,000 feet wasn't acceptable. It was catastrophic. Superchargers existed, of course. They had existed since World War I. A supercharger was essentially a compressor that forced more air into the engine, compensating for the thin atmosphere at altitude. Most American fighters used simple, mechanically driven superchargers, connected directly to the engine crankshaft. These devices worked, after a fashion, but they consumed enormous amounts of power to operate. The supercharger on a typical engine might consume 15 to 20% of the engine's output just to compress the intake air. At high altitude, you gained back some of the power lost to thin air, but you also paid a constant penalty for running the compressor. The net gain was modest, and the system had significant limitations. Mechanically driven superchargers were geared to work efficiently at specific altitude bands. A supercharger geared for low altitude would overboost the engine at high altitude, causing detonation and potential engine failure. A supercharger geared for high altitude would provide insufficient boost at low altitude, leaving the aircraft underpowered during takeoff and climb. Some manufacturers attempted to solve this with two-speed superchargers that could shift between low and high altitude gearing, but these added complexity, weight, and still only provided optimal performance at two specific altitude ranges. Johnson sat in his office reviewing performance charts that told a discouraging story. The XP-38 prototype, with its mechanically driven superchargers, could reach 20,000 feet, but it took nearly 15 minutes to get there. Once at altitude, the engines produced marginally better power than at sea level, but the superchargers themselves consumed so much energy that the net gain was disappointing. Maximum speed at 20,000 feet was barely 340 miles per hour, slower than many single-engine fighters, and completely inadequate for the fighter's intended role as a high-altitude interceptor. The Army Air Corps test pilots who had flown the prototype were diplomatic in their reports, but the message was clear. Without dramatic improvement in high-altitude performance, the P-38 would never see combat. The solution that Kelly Johnson proposed in March 1941 seemed to violate common sense. Instead of using engine power to drive the supercharger, he would use exhaust gases. The concept of turbocharging had been around since before World War I, invented by a Swiss engineer named Alfred Bucci. The principle was elegant. Piston engines waste enormous amounts of energy as hot exhaust gases. These gases exit the engine at high temperature and pressure, then dissipate uselessly into the atmosphere. A turbocharger captures this waste energy by routing the exhaust through a turbine wheel. The turbine spins at incredibly high speeds, driven purely by exhaust gas flow. This turbine is connected by a shaft to a compressor wheel on the intake side. The compressor forces air into the engine at higher pressure, compensating for altitude. Because the turbocharger is powered entirely by waste exhaust energy rather than engine output, it provides boost without the parasitic power loss of a mechanical supercharger. In theory, a properly designed turbocharged engine could maintain sea-level power output all the way to 30,000 feet or higher. In practice, turbochargers in 1941 were temperamental, unreliable, and generally considered unsuitable for fighter aircraft. The turbine wheels spun at speeds exceeding 20,000 revolutions per minute. At these velocities, any imbalance, any foreign object ingestion, any material defect could cause catastrophic failure. The turbine operated in an environment of extreme temperature, subjected to exhaust gases exceeding 1600 degrees Fahrenheit. Materials that could survive these conditions while maintaining precise tolerances were expensive and difficult to manufacture. The control systems required to manage boost pressure were complex and prone to failure. Most critically, turbochargers had significant lag characteristics. When a pilot opened the throttle, demanding more power, there was a delay while exhaust gas flow increased, spooling up the turbine to higher speeds before boost pressure rose sufficiently. In combat, where split-second throttle response could mean the difference between life and death, this lag was considered unacceptable. The American aviation establishment had largely abandoned turbochargers for fighter aircraft by 1940. The Navy had tried them on several designs and concluded they were too unreliable for carrier operations. The Army Air Corps had experimented with turbocharged versions of various fighters and found the maintenance requirements overwhelming. Most experts agreed that turbochargers belonged on large bombers, where the weight and complexity penalties were acceptable, and where steady-state, high-altitude cruise was more important than rapid throttle response, suggesting that a fighter aircraft, designed for violent maneuvering and demanding instant power response, should rely on turbochargers, struck many engineers as fundamentally misguided. Kelly Johnson was not most engineers. At 31 years old, he had already established a reputation for unconventional solutions to impossible problems. Born in Ishpeming, Michigan, the seventh of 9 children in a Swedish immigrant family, Johnson had put himself through the University of Michigan by working in factories and restaurants. His master's thesis on wind tunnel testing techniques had impressed Lockheed enough to offer him a position in 1933, during the depths of the Great Depression, when engineering jobs were nearly impossible to find. Johnson's approach to engineering problems was rooted in first principles rather than conventional wisdom. He would often tell his team, "Be quick, be quiet, and be on time." When analyzing the P-38's altitude problem, he ignored what aviation experts said couldn't be done and focused on what physics said must be possible. The mathematics of turbocharging were undeniable. An engine that maintained full power to 30,000 feet would revolutionize high-altitude combat. The tactical implications were staggering. Such an aircraft could climb faster than any enemy fighter, operate at altitudes where interceptors couldn't reach, dive from above with devastating energy advantage, and maintain cruise speed at altitudes where conventional fighters struggled to even remain airborne. The question wasn't whether turbocharging would provide overwhelming advantage, The question was whether Johnson could solve the technical problems that had defeated every previous attempt to make turbochargers work on fighter aircraft. The engineering challenges were formidable. First, the turbocharger installation had to fit within the P-38's unique twin-boom configuration. Each engine nacelle would need to house not just the Allison engine, but also a turbocharger, intercooler, ducting, and control systems. The packaging was nightmarish. Second, the turbocharger had to survive combat conditions. Fighter aircraft pulled high G loads during violent maneuvering. They operated in temperature extremes from tropical heat to Arctic cold. They absorbed battle damage and continued flying. Any turbocharger installation had to be robust enough to function reliably under these conditions. Third, the control system had to be simple enough for pilots to manage during combat. Complicated boost management systems that required constant attention would be useless in the chaos of aerial battle. Johnson assembled a small team of engineers who shared his conviction that the seemingly impossible could be made to work. They began by studying every turbocharger failure mode documented in previous installations: turbine wheel failures due to material defects, bearing failures from inadequate lubrication at high speeds, control system failures from vibration, ducting failures from thermal expansion. Each failure mode was analyzed and solutions were designed. For turbine wheel reliability, Johnson specified General Electric turbo superchargers, built to specifications, normally reserved for industrial applications. These units used turbine wheels machined from high-nickel alloy steel, carefully balanced to tolerances measured in thousandths of an inch. Each turbine was individually tested at operational speeds before installation. The bearing systems used pressure-fed oil lubrication with dedicated oil coolers to manage the extreme temperatures. The intercooler problem was particularly challenging. Compressing air generates heat. The compressed air coming from the turbocharger might be at high pressure, solving the thin air problem, but it would also be at elevated temperature. Hot air is less dense than cool air, reducing the mass of oxygen entering the engine and limiting power output. To maximize performance, the compressed air needed to be cooled before entering the engine. This required an intercooler, essentially a radiator for intake air. But intercoolers were large, heavy, and created aerodynamic drag. Installing them in the already crowded engine nacelles seemed impossible. Johnson's solution was to mount the intercoolers in the leading edges of the wings, using ram air from the aircraft's forward motion to cool the compressed intake air before it reached the engines. This unconventional placement used otherwise wasted space and turned the aircraft's speed into an advantage. The faster the P-38 flew, the more efficiently the intercoolers worked. The ducting system that connected turbocharger to engine to intercooler was a nightmare of thermal expansion problems. Exhaust ducting carrying 1600-degree gases would expand significantly during operation. Intake ducting, carrying pressurized air, had to maintain leak-free seals while accommodating vibration. Johnson's team designed flexible joints and expansion bellows at critical points, using materials and techniques borrowed from industrial boiler applications. Each joint was tested under conditions exceeding expected operational stresses. The control system was kept deliberately simple. The pilot had a single throttle quadrant that controlled both engine power and turbocharger boost. An automatic wastegate valve regulated exhaust gas flow to the turbine, maintaining proper boost pressure without pilot intervention. In combat, the pilot could focus on flying and fighting, trusting the turbocharger system to maintain optimal engine performance automatically. By summer 1941, the first P-38E model with fully functional turbocharger installation was ready for testing. The aircraft sat on the ramp at Lockheed's Burbank facility, its distinctive twin-boom design gleaming in California sunshine. Test. Pilot Ralph Verdon climbed into the cockpit for the initial high-altitude performance evaluation. The test plan called for a climb to 30,000 feet, then level acceleration runs to determine maximum speed. As Verdon advanced the throttles for takeoff, the Allison engines roared to full power, but instead of the usual power loss as the aircraft climbed, the turbochargers maintained manifold pressure. At 5,000 feet, the engines were still producing 1,150 horsepower each. At 10,000 feet, power remained constant. At 15,000 feet, where the P-38 prototype had begun gasping for air, the turbocharged engines continued pulling strongly. At 20,000 feet, Virden leveled off and pushed the throttles forward for a speed run. The P-38 accelerated smoothly, building speed with none of the sluggishness that characterized high-altitude flight in other fighters. The airspeed indicator climbed past 350 miles per hour, then 370, then 390. At 410 miles per hour, Virden eased back on the throttles and radioed the test results to the ground. The turbocharged P-38 had just exceeded 400 miles per hour at 20,000 feet, making it one of the fastest aircraft in the world at that altitude. More importantly, the engines had maintained full power throughout the climb, arriving at altitude with energy reserves that would give the Lightning overwhelming tactical advantage. Virden continued climbing. At 25,000 feet, the turbochargers continued maintaining manifold pressure. The engines roared with the same authority they had shown at sea level. A speed run at this altitude produced results that shocked even Johnson's optimistic team. 420 miles per hour at 25,000 feet, an altitude where most contemporary fighters could barely maintain 300 miles per hour. The implications were staggering. At 30,000 feet, conventional wisdom said aircraft performance degraded to marginal levels. Virden climbed to 30,000 feet and found the P-38 still flying strongly. The turbochargers were maintaining sufficient boost to keep the engines producing usable power. A speed run at 30,000 feet yielded 390 miles per hour, faster than most fighters could fly at their optimal altitude. The turbocharged P-38 could operate effectively in atmospheric conditions that rendered other aircraft nearly helpless. The Army Air Corps test pilots who evaluated the turbocharged P-38 filed reports that read like promotional literature. The aircraft climbed to 20,000 feet in under 7 minutes, half the time required by the prototype. It maintained maximum speed across an altitude band from sea level to 30,000 feet, giving pilots flexibility to choose whatever altitude provided tactical advantage. The engines responded instantly to throttle inputs with no appreciable turbo lag, providing the throttle response essential for combat maneuvering. Most significantly, the turbocharged P-38 could operate at altitudes where enemy fighters simply could not follow. A pilot being pursued by enemy aircraft could simply climb into thin air where his turbochargers continued functioning while his opponent's engines suffocated. The technical achievement represented by Johnson's turbocharger installation cannot be overstated. He had taken a technology that experts considered unsuitable for fighter aircraft and made it not just functional but transformative. The key was not any single innovation, but rather the integration of multiple engineering solutions into a coherent system. The robust turbo-supercharger units that could survive combat conditions, the innovative intercooler placement that cooled compressed air without aerodynamic penalty, the flexible ducting that accommodated thermal expansion and vibration, the automatic control system that required no pilot intervention. Each element was essential, and together they created a propulsion system that fundamentally changed what was possible in aerial combat. Production of turbocharged P-38 models began in earnest in late 1941. The E model gave way to the F model with minor improvements, then the G model with enhanced turbocharger controls. Each variant refined Johnson's basic design, but the fundamental turbocharger installation remained essentially unchanged from his original concept. By December 1941, when America entered World War II, Lockheed was producing P-38 Lightnings at a rate that would eventually reach 10 aircraft per day. Every single one featured Kelly Johnson's supposedly impractical turbocharger system. The mechanics and ground crews who maintained these aircraft in combat conditions initially viewed the turbochargers with suspicion. Complex systems usually meant maintenance nightmares, and the turbo-supercharger installation looked complicated indeed. But combat experience quickly proved the system's reliability. The turbine wheels, machined to such precise tolerances, proved remarkably resistant to combat damage. The oil cooling systems kept bearings functioning even in tropical heat. The automatic wastegate valves regulated boost pressure without requiring adjustment. Maintenance crews discovered that routine turbocharger inspections took less time than the valve adjustments required on mechanically supercharged engines. The system that looked complex on the engineering drawings proved straightforward in practice. Pilots transitioning to the P-38 from other fighters initially worried about managing the turbocharger systems during combat. They expected complicated boost controls, constant monitoring of manifold pressure, and the risk of overboosting the engines during violent maneuvering. Instead, they found Johnson's automatic control system handled everything. The pilot advanced the throttle, and the turbochargers provided whatever boost was necessary to maintain optimal engine performance. During combat maneuvering, as the aircraft pulled G-loads and changed altitude rapidly, the wastegate valves adjusted automatically to maintain proper boost pressure. Pilots could focus entirely on tactics and gunnery, trusting the propulsion system to deliver consistent power. The true genius of Johnson's design became apparent when P-38s encountered enemy aircraft at high altitude. Japanese pilots flying Mitsubishi Zeros discovered that their vaunted fighter, so dominant in horizontal maneuvering combat below 15,000 feet, became increasingly helpless as altitude increased. At 25,000 feet, a Zero's engine was producing perhaps 600 horsepower, while the P-38's turbocharged Allisons were still generating over 1,100 horsepower each. The power-to-weight ratio shifted dramatically in the Lightning's favor. More critically, the Zero pilot knew that climbing higher would only worsen his disadvantage, while the P-38 pilot could climb indefinitely, always maintaining superior power output. German pilots in Europe faced the same cruel reality when P-38s began escorting bombers over occupied territory. The Messerschmitt Bf-109 and Focke-Wulf Fully 190, excellent fighters with sophisticated mechanically supercharged engines, found themselves outclimbed and outrun by the turbocharged American fighter. At 30,000 feet, where German interceptors struggled to maintain formation, the P-38 operated comfortably, with power reserves that allowed aggressive maneuvering. Luftwaffe pilots learned to avoid engaging Lightnings at high altitude, seeking lower altitudes where their fighters' superior handling characteristics might provide some advantage. But the P-38 pilot always held the option to simply climb away from any unfavorable engagement, knowing his turbochargers would continue functioning long after his opponent's engine was gasping for air. The strategic implications extended far beyond individual combat. The turbocharged P-38 could escort bombers to targets previously considered beyond fighter range. The aircraft could maintain cruise power at high altitude for hours, while mechanically supercharged fighters burned excessive fuel fighting to maintain altitude. This translated to combat radius exceeding 1,000 miles with external fuel tanks, allowing P-38 escorts to accompany bombers throughout their entire mission profile. Bomber crews who had previously faced the terrible choice between flying without escort or aborting deep penetration missions now had protection throughout their most dangerous operations. The reconnaissance photographs arrived at 5th Air Force Headquarters in Brisbane, Australia, in early April 1943. Shot from 32,000 feet by an 5 photographic Lightning, the images showed Japanese airfields across Rabaul with unusual clarity. What made these photographs remarkable wasn't just their quality, but the altitude from which they were taken. No Japanese fighter had even attempted to intercept the reconnaissance aircraft. They couldn't reach it. The photo Lightning had cruised above Rabaul for 40 minutes, its turbocharged engines maintaining full power while Japanese pilots watched helplessly from below, their aircraft unable to climb high enough to engage. This single mission captured the revolution Kelly Johnson's turbocharger system had created. The aircraft that experts had dismissed as too complicated for combat operations was now operating with impunity over the most heavily defended Japanese base in the Southwest Pacific. But the true measure of Johnson's achievement wasn't found in technical specifications or altitude records. It was written in the survival rates of American pilots and the changing calculus of aerial warfare. In the first 6 months of 1943, P-38 squadrons in the Pacific Theater achieved kill ratios that would have seemed impossible a year earlier. The 49th Fighter Group, operating turbocharged Lightnings from New Guinea, claimed 137 Japanese aircraft destroyed against 11 P-38s lost in aerial combat. The mathematical advantage was overwhelming, but behind those numbers lay a profound human reality. American pilots were coming home. Young men who 6 months earlier would have been forced into desperate turning fights against superior maneuvering enemy aircraft now possessed the ability to dictate every aspect of combat. They could choose when to engage, from what altitude, at what speed, and most critically, when to disengage if conditions became unfavorable. The psychological transformation was as significant as the tactical advantage. Lieutenant Robert de Haven, a P-38 pilot with the 49th Fighter Group, recorded his impressions in a letter home to California in May 1943. His words captured what Kelly Johnson's engineering had meant to the young men who flew combat missions over hostile territory. "We climbed to 30,000 feet before crossing the coast," de Haven wrote. "Up here, the engines still have power. The Zeros can't touch us. We pick our targets, dive down with all that altitude advantage, make our attack, and climb right back up. They can't follow. They can't catch us. For the first time since this war started, we have the advantage." De Haven would survive the war with 14 confirmed victories, but more importantly, he would survive. The turbocharger system that gave his P-38 maintained power at extreme altitude had quite literally saved his life dozens of times by providing options that other fighters simply didn't possess. The Japanese response to the turbocharged P-38 revealed the desperation of facing technological inferiority that couldn't be overcome through courage or skill. Intelligence reports captured after the war showed that Japanese aircraft designers had attempted to develop their own turbocharged fighters. The Kawasaki Ki-64 prototype incorporated a turbocharger system copied from a crashed P-38, but Japanese industry lacked the manufacturing precision to produce turbine wheels that could survive operational conditions. The bearings failed after a few hours of operation. The turbine wheels developed cracks and disintegrated at high speeds. The metallurgy and machining tolerances that American industry took for granted were beyond Japan's industrial capacity in wartime conditions. Even when Japanese engineers understood exactly what was needed, they couldn't manufacture it. This wasn't a failure of intelligence or courage. It was the brutal reality of industrial capacity determining combat outcomes. By mid-1943, the turbocharger advantage had become so decisive that it began influencing strategic planning at the highest levels. General George Kenney, commanding the 5th Air Force in the Southwest Pacific, designed entire campaigns around the P-38's high-altitude capabilities. Bomber strikes could be planned against targets previously considered too distant or too heavily defended, knowing that turbocharged Lightning escorts could protect them throughout the mission. The range advantage was particularly significant. While escorting bombers, the P-38s cruised at 25,000 feet, where their turbocharged engines operated with maximum efficiency. Fuel consumption at high-altitude cruise was actually lower than at medium altitude, because the engines ran at lower power settings while the turbochargers provided boost. This counterintuitive benefit meant P-38s could escort bombers deeper into enemy territory than any other Allied fighter, fundamentally changing what was operationally possible. The April 18, 1943 mission that intercepted Admiral Yamamoto over Bougainville demonstrated how completely Kelly Johnson's turbocharger system had transformed strategic possibilities. The mission required a 435-mile overwater flight from Guadalcanal, precise navigation without landmarks, perfect timing, and enough fuel reserve to return home after combat. Only the P-38 possessed the combination of range, speed, and reliability to accomplish this mission. 16 Lightnings took off before dawn, their turbocharged engines pulling them smoothly to cruise altitude. They flew for over 2 hours at wave-top height to avoid radar detection, then climbed to intercept altitude just minutes before Yamamoto's aircraft arrived. The turbos spooled up smoothly, maintaining power as the Lightnings climbed from sea level to 18,000 feet in minutes. When Captain Thomas Lanphier and Lieutenant Rex Barber rolled into their attack, they had full engine power available. Their victims, the Mitsubishi G4M Betty bombers carrying Yamamoto and his staff, had no chance. The turbochargers that had seemed like an overcomplicated solution to a simple problem had enabled one of the most significant precision strikes in military history. The human cost of Japan's technological disadvantage became increasingly visible as the war continued. Japanese pilot training programs, already abbreviated due to fuel shortages, now had to prepare young pilots for an aerial battlefield where they would be fundamentally outmatched. Training manuals captured after the war contained instructions that revealed the desperation. Avoid combat with P-38 above 20,000 feet. Do not attempt to climb after P-38 that is disengaging. Engage only when numerical superiority exceeds 3-to-1 and altitude advantage is secure. These weren't tactical guidelines. They were admission that Japanese pilots could no longer fight on equal terms. Young men were being sent into combat, knowing they possessed inferior equipment, with instructions that essentially amounted to avoid the enemy's best fighter whenever possible. The psychological burden of this situation, combined with the physical danger, created unbearable stress. Letters and diaries recovered from Japanese units showed pilots struggling with the knowledge that they were being systematically outclassed by American technology. One letter, written by a Zero pilot in the 204th Air Group and captured after the Battle of the Philippine Sea, described watching P-38s attacking from above. They come from so high we cannot see them until they are diving. By the time we see them, they are too fast to track. We turn to meet them, but they are already climbing away. We climb after them, but our engines lose power and we fall back. They climb above us, again, and attack again. There is nothing we can do. This wasn't a failure of courage. The writer of this letter had fought since the war's first day, had flown over Pearl Harbor, and had survived the campaigns in the Dutch East Indies and the Solomons. But courage couldn't overcome the fundamental power differential created by Kelly Johnson's turbocharger installation. The letter's author died 2 weeks later, shot down by a P-38 over Guam. He was 23 years old. The industrial dimension of Johnson's achievement became even more significant as production accelerated. Lockheed's Burbank factory, initially producing 10 P-38s per day, had increased production to nearly 15 aircraft daily by late 1943. Each Lightning required 2 turbo supercharger units, manufactured by General Electric in New York, intercoolers produced in California, and thousands of precision components from suppliers across America. The supply chain that supported P-38 production involved tens of thousands of workers, from the women machining turbine wheels in General Electric factories to the engineers designing improved intercooler cores at Lockheed. This distributed manufacturing capability, with quality control maintained across hundreds of suppliers, was something Japanese industry simply couldn't replicate. Even if Japanese designers had solved all the technical problems, their industrial base lacked the capacity to manufacture turbocharged fighters in meaningful numbers. By 1944, the accumulated advantage of Johnson's turbocharger system had created aerial supremacy that extended beyond tactical combat. Photo reconnaissance Lightnings mapped every Japanese installation in the Pacific. They flew over defended targets at 35,000 feet, photographing airfields, harbors, and defensive positions with impunity. Japanese anti-aircraft guns couldn't reach these altitudes effectively. Fighter interceptors couldn't climb high enough before the fast-moving fives completed their photo runs and departed. The intelligence gathered by these high-altitude reconnaissance missions enabled precision targeting that multiplied the effectiveness of every subsequent attack. Bomber crews knew exactly where to find their targets. Fighter sweeps knew where Japanese aircraft were based. Naval commanders understood the disposition of enemy ships and coastal defenses. All of this was made possible by turbocharged engines that maintained full power at altitudes where conventional aircraft couldn't operate. The P-38's contribution to the strategic bombing campaign over Europe demonstrated another dimension of Johnson's achievement. When Lightnings began escorting heavy bombers over Germany in late 1943, Luftwaffe fighter tactics had to adapt to an enemy that couldn't be outclimbed or outrun at altitude. German fighter controllers had developed sophisticated tactics for attacking, bomber formations, typically approaching from high altitude to dive through the formation, attacking from multiple angles to split defensive fire. These tactics assumed that American fighter escorts would be unable to maintain position at bomber altitude during violent defensive maneuvers. The P-38 violated this assumption. Its turbocharged engines maintained full power at 25,000 feet, allowing escort pilots to position above the bombers and engage German fighters with altitude advantage. Moreover, when German fighters dove away after their attacks, the Lightnings could follow them down at speeds the German aircraft couldn't match, then climb back to bomber altitude without the extended recovery time required by mechanically supercharged fighters. The human stories of survival multiply across the European theatre as well. Bomber crews who had watched fighters fall away as they climbed to bombing altitude, leaving them vulnerable during the most dangerous portion of their mission, now had escorts that stayed with them from takeoff to landing. The psychological reassurance of seeing P-38 silhouettes above the formation, knowing those twin-boomed fighters had the altitude performance to engage any threat, transformed the bomber crew's experience of deep penetration missions. Second Lieutenant Robert Morgan, a B-17 pilot, wrote in his mission diary about a raid on Regensburg in August 1943. "The Lightnings stayed with us all the way. When German fighters tried to hit us at 27,000 feet, the P-38s were above them, diving down. It was the first time we'd seen American fighters mixing it up at that altitude. Some of the crew actually cheered over the intercom." Morgan and his crew completed their tour of duty. They came home. The turbocharged engines that kept the P-38s operating effectively at extreme altitude had protected them during their most vulnerable moments. The technical evolution of the turbocharger system continued throughout the war. The P-38J model introduced war emergency power settings that allowed temporary overboost for combat situations, pushing engine output to 1,350 horsepower per engine at emergency boost. The system remained reliable even under these enhanced power conditions, a testament to the engineering margins Johnson had built into the original design. The L model incorporated improved automatic controls that adjusted boost pressure even more precisely during combat maneuvering. Each refinement made the system more effective, but the fundamental design remained essentially unchanged from Johnson's 1941 concept. He had gotten it right the first time. The war's conclusion in August 1945 found P-38 Lightnings operating over Japan itself, their turbocharged engines maintaining full power at altitudes where Japanese defenders could mount only token resistance. The aircraft that had seemed too complicated for combat operations had proven itself in every theatre of the war, from the deserts of North Africa to the frozen skies over the Aleutians, from the jungles of the Southwest Pacific to the industrial heartland of Germany. Kelly Johnson's supposedly impractical turbocharger system had operated reliably under every conceivable condition, validating his conviction that revolutionary solutions were worth the engineering challenges they presented. The post-war analysis of the P-38's contribution to Allied victory consistently emphasized the turbocharger system as the defining feature. Without the ability to maintain power at high altitude, the Lightning would have been just another twin-engine fighter, interesting but not transformative. With turbocharged engines that could operate effectively above 30,000 feet, it became the aircraft that redefined what was possible in aerial warfare. General Henry Hap Arnold, commanding general of the Army Air Forces, stated in his post-war report that the P-38's high-altitude performance had been decisive in achieving air superiority in both theaters. This was remarkable praise from a commander who had access to many excellent aircraft designs. Arnold recognized that Johnson's turbocharger installation hadn't just improved one aircraft's performance. It had changed the nature of aerial combat itself. Kelly Johnson himself remained characteristically modest about the achievement. In interviews decades later, he would describe the turbocharger decision as obvious once you understood the physics. But the hundreds of engineers who had declared turbocharged fighters impractical would disagree. The obvious solution is only obvious in retrospect, after someone has the vision and determination to make it work. Johnson possessed both qualities. He saw what was possible, understood what was necessary, and refused to accept that complexity was an insurmountable barrier to revolutionary performance. The human legacy of Johnson's work extends beyond statistics and technical achievements. Every pilot who survived because his P-38 could climb away from a dangerous situation owed his life to those turbochargers. Every bomber crew that returned home protected by high-altitude Lightning escorts owed their survival to maintained engine power at extreme altitude. The families who welcomed home fathers, brothers, and sons who might otherwise have been lost represent the true measure of engineering achievement. Technology that saves lives, that gives courageous young men the tools to survive, combat, and return home, that transforms desperate fighting into manageable missions with reasonable survival odds, represents engineering at its most meaningful. The Japanese pilots who faced turbocharged P-38s deserve their own recognition. They fought with tremendous courage against overwhelming technological disadvantage. Many understood, perhaps better than their commanders, that they were being asked to achieve the impossible. They flew obsolete aircraft against superior opponents, knowing the likely outcome because their culture demanded sacrifice and their duty required it. The tragedy wasn't their lack of courage or skill. The tragedy was that their nation's industrial limitations made it impossible to provide them with equipment that would have allowed their courage and skill to matter. The letters these young men wrote home, the diaries recovered from crash sites, the post-war interviews with survivors, all testify to the human cost of technological inferiority. The broader lesson of Kelly Johnson's turbocharger achievement extends far beyond World War II aviation. It speaks to the power of refusing to accept conventional wisdom when physics suggests a better solution exists. It demonstrates that complexity, properly managed, can create capabilities that simple solutions cannot match. It shows that revolutionary advances often come from engineers willing to solve hard problems rather than accepting easy limitations. Every generation faces technological challenges that experts declare insurmountable. Every era has conventional wisdom that constrains what seems possible. Johnson's work reminds us that these barriers often exist not in reality but in imagination, waiting for someone with sufficient vision and determination to prove they can be overcome. The P-38 Lightning flew its last combat missions in early 1946 as occupation forces replaced combat units throughout the Pacific. The aircraft that had shocked Japanese pilots with its speed and altitude capability was retired from frontline service, replaced by jets that would take aviation into a new era. But the principles Johnson had proven remained fundamental. High-altitude performance mattered. Power at altitude determined tactical options. Technology properly applied could create decisive advantage. These lessons influenced every subsequent generation of military aircraft. The jets that replaced the Lightning incorporated turbocharging principles in their engine designs. Modern fighters operate at altitudes the P-38 could barely reach, but they do so using the same basic principle Kelly Johnson proved in 1941: maintain power output regardless of atmospheric conditions, and tactical advantage follows. Museums worldwide preserve P-38 Lightnings, their distinctive twin-boom configurations still recognizable 8 decades later. Restored examples fly at air shows, their turbocharged Allison engines still capable of demonstrating the performance that changed aerial warfare. Veterans gather at these displays, sharing stories of missions flown and friends lost. Young people asked questions about what it was like to fly these aircraft in combat. The veterans described the confidence that came from knowing their Lightnings could outclimb, outrun, and outfight anything the enemy could send against them. They remember the sound of those turbocharged engines at full power, the feeling of climbing through 30,000 feet with power to spare, the satisfaction of having technological superiority that made survival possible. These memories, shared across generations, preserve not just history but understanding of what engineering excellence means in human terms. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.